So here we're going to talk about the physical principle for three major porosity measurement methods, porosimetry of NMR, BET, and helium. Three commonly used. The first is a graph from Schellenberger, which is the most authoritative source for NMR interpretation. And you can see in this plot the signal only span from a millisecond to beyond, and they were matching the bed diameter, the pore diameter of tenths of nanometer to 100 nanometer and beyond. And the free fluid cutoff is at 33 milliseconds. This might be a little bit flexible for different rocks and different fluids. For water and oil, heavy oil, might be different, but overall it's approximately in this range. And so this side is called free fluid, and this side from 1 millisecond to tenths of a millisecond is called bounded. And the interpretation could be anywhere from clay bounded to capillary bounded to heavy oil or movable oil, or light oil. This could all change to different reservoirs. But overall, you can't use it beyond, well beyond 1 millisecond, which is tenths of nanometer. Anything below that, the NMR just disappeared. The signal just decayed and completely disappeared after 10 nanometer. But for unconventional resources, a lot of the porosity are actually below 10 nanometer, as we shall see. And also for gas, shale gas, the signal is much weaker, so you can't use it effectively. And so BET is another important posimetry method that change the temperature and measure the amount of deposition or phase change of nitrogen or CO2, and you can measure the surface area as well as characterize the nanoporosity. It's best used after 100 nanometer, and you can see that it really works well best when the size of the porosity is under 50 nanometers, matching here. So this is a very complementary method to NMR BET. It's a complementary part of the NMR. And so helium posimetry, on the other hand, measures anything that's accessible with free gas. If it has porosity sealed off by a salt or other process, a lot of the unconventional, you need water to open up this nano porosity, then helium posimetry can't measure it. That's why we see many porosity data measured with helium posimetry are really low, ridiculously low, can't match the porosity. We're going to talk about the density difference-based posimetry, or DDP. So DDP is like based on the same principle like Archimedes compared the gold crown density versus true gold density, where he used the buoyancy to measure the volume and then compare the weight of the crown versus true gold, and the difference is the porosity. Similar method already used in wireline logging, where we compare the lithology density versus neutron density will give us the porosity. So we developed a new unique DDP for cuttings. Note this can be working for cuttings. So no need for expensive core or rare to get, hard to get. And but we can also measure cores, which will include micro porosity, larger porosity. And this DDP for cuttings is focusing on the nano porosity, as we talked about, and suitable for all drilling fluid, whether it's oil-based mud or water-based mud. So it can be applied for both vertical pellet well as well as lateral production well, and low cost and widest application, whether it's gas or oil. So here is an example. So this is the PVD of a pellet well in Permian, and the porosity DDP measured by DDP method is shown here in the blue data points. We could see the decrease of porosity in the first 6,000 feet, or 2,000 meters due to compaction subsidence. And then nanoporosity developed in the Wolfcamp and Bone Springs. And as the maturity increase and oil and gas generation. So this is clear shows the effectiveness of our method.